All right. So welcome to, all right, it's going to be a lot of fun today, I guess. I don't know. Are we close to quantum physics? No, the quantum physics is not included in this course. So unfortunately, all right, if you really want to get some taste of quantum mechanics, then you have to, I think, is there any like physics 3? I think maybe. Or maybe just, I don't know, come to physics major, maybe. I was just kidding. I think there you need to take another one, I think, to get to quantum physics because the last topic in this course is magnetism, I think, something like that, somewhere around there. So it's electromagnetic waves. That's the last part of it. So I don't think you can get some quantum physics here. And for all right, so that's what it is. All right, guys. So just download the handout number 7. I think I put number 8 in there as well. So you can download number 7 and then just all right. This is going to be the hardest part of the course. I don't know what to tell you, but it's the combination of everything that you have done in the past. It's going to come together here. So that means you're going to get a sort of like calculus. I mean, I know you've been waiting for this. So it's eventually arrive here. But as I said, there's some extra with no extra charge here. It means that I'm going to put calculus in combination with vectors. So what are you about to experience in the next few lectures are vector calculus problems. That's going to be a lot of fun. All right, so what we are going to do today is first, let's bring you guys back to vectors problem. All right, you have done a lot of vectors calculations in Newtonian physics, right? That's what you have been doing. You do like the vector components, you have the force, you're breaking the force into 2 components, whatever 3 components, and then you do maybe sigma F equal to ma, or you do equilibrium analysis and all this stuff. Now we have another kind of vector, and it's going to be something related to another like main categories in physics. It's electricity and magnetism. All right, and that's what it is. I don't have any sound effects today either. So, all right, you're supposed to have like a big applause right here, but it's not. All right, so what are we about to do? This is sort of like the way that they arrange the material. It seems like electric field or electric force or anything related to electric, it seems to be easier to comprehend than magnetic. I don't know, maybe it's just the way that this theory has been theorized, and then they started everything from, I mean, it's a historical reason that they've sort of get the feeling of electric stuff easier than magnetic stuff. So this is why they sort of came up with the idea of how to explain electric phenomena first. That's why the approach seems to be more straightforward than the magnetic. All right, and the magnetic actually it's sort of like have a funny behaviors that needs some extra vectors analysis on top of the one that you have been doing in the past. So that's what we are about to attack first. We're going to look at electric field. This is the one, field. And of course, the big category that you have to deal with is the electric force. Okay, so this is another force of nature that you're about to learn right here. Okay, so now we have gravity. We had what? Of course, push and pull, and we don't care that much. Now, this is electric force. All right, and in the future, then you might have like a nuclear force. You might have some other forces, but now we are in the sort of like in the area that we would like to talk about electric as the main stuff here. So we are about to talk about charges. You probably have heard of this many times, but today's key topics is going to be electric field and then electric force. All right, so let me sort of like explain to you here a little bit first. In the textbook, they will introduce electric force first, and the law that allow you to calculate forces quantitatively is by using Coulomb's law. So these two come together. Okay, so you're going to learn another law, and that's a Coulomb's law. However, it seems to me from what we have been, I don't know, I mean, I have been doing this for I don't know, decades maybe. It seems like it seems more natural to talk about fields first. And once you understand what the field is, getting to the electric force is like a piece of cake. Or maybe it's just hard to chew cake, but it's a cake anyway. So, I mean, if you can go through how to calculate all those fields, doing the force is going to be very simple. It's like sort of like some cherry on top or whatever. You just like, you know, put something on the top and then you call it done. It's like beautiful already. All right, sounds good. So that's what we're about to do today is the electric field. And let's see how far I can take you guys to understanding this kind of thing. Sounds like a plan? All right. I don't know, have you guys had any experience with the electric field calculation at all? Electric forces, Coulomb's law, have you heard this in the past? If you have done some physics in high school in the topic of electricity, you probably have heard of this Coulomb's law already. I think maybe once or twice. Is that right? Oh, maybe not. All right. If not, that is okay. All right. And there's a question comes in electromagnetism. Yeah, eventually. So the grand finale of this one is it turns out electric and magnetic, they are closely related. They are relatives somehow. So if you can generate one, you automatically in general generate the other. So they pretty much cannot be separated. And that's the reason why you are getting electromagnetic waves and all this stuff at the end. Okay. All right. So let's dive into it, guys. So I think I'm not going to introduce too much about like history and all this stuff, but it's already in our nature without, I mean, well, it's our universe here. So too bad it's there. And I think this story just sort of like take you back to the time of Benjamin Franklin, who did some experiments, and like you have like a lightning strike or all this stuff, and then he sort of get some experiment and sort of like observe that in nature there are two types of the thing that can sort of like that can showcase all these weird behavior. He names those stuff like charges. All right. And somehow after some experiments, he can classify these charge into two types. One is he names positive. All right. And the other that he calls is like opposite to that. He said is, all right, let's call this type negative. Okay. So that's why you get positive and negative charge. All right. There are two things that you probably just have to sort of like put a note into it. It turns out, I mean, from our modern knowledge and everything, that charge is not a continuous number. This is the weirdest stuff that could happen to you at this time. I mean, at this lecture here. It turns out charge in this universe, okay, we have a name for it. It's called quantized. But what it means is it is a discrete number. So that means in this universe, it's always a multiple of these numbers right here. It turns out this number is the charge of one electron. That's why we call this an electronic charge. So that means any charges that you're going to experience in whatever in your life and everything is going to be multiple of these numbers. Isn't that weird? So that means it seems like the electronic charge or this constant right here seems to be like a fundamental numbers of this universe that's everything else is going to build on top of this. That's weird. All right. And everyone now knows that this is the charge of electron. Okay. And electron is just like elementary particles that's lying around, sort of like orbiting around atoms, molecules, and all this stuff flowing in the electrical wires and everything. So it seems like we are dealing with electrons all the time. Okay. And it turns out it's right. Okay, that's a good comment. That's your friend just talked about. Like, what about proton? Proton is also another fundamental particle there. But it turns out the proton is much more heavier. So that's why it's going to have less effect in everything else. For example, electricity that you use in your electrical devices, in your household, whatever power consumption that you talk about using electricity, everything is just responsible by electrons. Because they're so light, the mass is super small, it virtually has no size. It's weird. I mean, no one has ever talked about the size of electrons. So that's why it can move, it can travel, it can transfer very easily. And that's why this is like a fundamental particles that has a lot of effects. And you already knew that the structure of the periodic table due to the arrangement of the electrons around nucleus. So that's why we can say this electron is has more utilizations, I would say, than proton and other stuff, even though they are equally important, of course, right? An atom cannot be created without proton and electrons and neutron and all that stuff. But seems like electron is more versatile. It's like you can find out everywhere that you are dealing with electrons all the time, okay? And this is the number to take home with today, 1.6 times 10 to the negative 19, approximately. But it's a constant of the new universe, guys. I mean, it is it. So that means in this universe, if you would like to have a charge of, let's say, 1.7 times 10 to the negative 19 Coulomb, it doesn't exist. Isn't that weird? It's like, what? I cannot just pick any charge that you want. No, it has to be multiple of these numbers. Even though, of course, for those of you that have heard of like a fractional charge, for those, some of you that talk about like quark and that stuff, but anyway, it's still like some multiple of this number anyway. You cannot just like, okay, I'm gonna pick one crazy random number and then just put a charge on it. That's not possible. Okay, so that's one thing to take, is just there is a constant in the universe, and that constant is the numbers that give you the magnitude of charge of an electron. That's a number that we're going to use a lot, all right? And every time that you write E, sort of like it's universal. Everyone knows you talk about the electronic charge. Okay, sounds good? All right, so that's good. So the units of charge we name after Coulomb himself, who sort of like come up with the law and all that stuff. So the unit of charge is Coulomb. So we're going to say that one electron carries 1.60219, those numbers, times 10 to the negative 19 Coulomb of charge. So that means 1 Coulomb is huge. But when you say huge, it's not that bad. Well, it's not that bad in the sense that you will need about like 10 to the 19 electrons to give you a Coulomb of charge. But even though we say 10 to the 19 seems to be a big number, but we have already talked about thermodynamics, and that number is not that bad. It's like, you know, you have seen like 1 mole of gas already. It's already like 10 to the 23rd, 26. That's not bad. So talk about everything. I mean, something that's so small like that, you are sort of like familiar with 10 to the 20th, 10 to the 21st, and everything. It's so simple. All right. So although 1 Coulomb is big, but it's not that big. All right, it's supposed to have some sound effects here, but all right, I don't have that. Okay, second things to take home here is, well, this is an unfortunate, how can I say it? It's unfortunate pick, I guess. Benjamin Franklin decided to pick negative and positive without knowing the fundamental or elementary particles and whatever at the time. So he just picked one to be positive and one to be negative. And unfortunately, when they say what unfortunate, it means he picks electrons to have a negative charge. So that's why nowadays, every time you have an electron traveling, you have a negative charge traveling. So that's why every time that you would like to talk about something that is positive, you have to flip the directions all the time. You will see this in the near future. So from now on, when you have like a current flow, every time that you're doing something, you assume everything is positive, right? Because we always familiar with positive stuff. But now you have to understand that that's positive flow of the current will correspond to the negative flow, which is the opposite direction of the electrons. That's the weird stuff. All right. Okay, there's a question comes in. The big C, capital C is Coulomb and small c is light speed. Yes, that's pretty common. Yes. And I think the positions will separate them anyway, because you use the capital C as a unit. So it's going to come as like an after a number. And the small c is a constant the light speed. So usually you put it on the left in the sentence or whatever in an equation. So it should be fine, right? So it's the positions of those two characters are pretty much, it's at an obvious places already. Okay, all right, cool. So that's sort of like a grand introduction to what we are about to do. But anyway, what I would like you to think about this topic over here, for those of you that sort of like, you know, unfamiliar with the stuff, you can imagine of charge to be as important as mass. Think of it that way. All right. And sometimes you don't want to go too deep about like what is mass or what is how to generate mass. Or let's say that it's already here, it's already exists in our universe, and just move on. Just like, okay. So think of it like charge is already here. All right. Don't even ask like, Ajahn, how can you create electrons? Or, all right. So there will be like, you know, you have to go to like particle physics and all this stuff, like, you know, quantum chromodynamics and all this stuff. So don't worry about it. All right. Just say that it's a fundamental building block of a universe, which is not only mass, now you have charge. And second thing is, you already heard about the gravitational field or the gravitational attractions between masses. So every time you have two masses, they already have a pulling force. Yeah, it's like, you heard of this? AG M1 M2 over R squared. So that is a gravitational force acting between two masses. Same thing that you're going to experience right here. You're going to have an equivalent formula for that. So it turns out all those charges will interact with each other as well. So that's why it's sort of like super parallel between these two. Everything that you have done in the mass and interactions between them, you're gonna get exactly the same thing here with the charge. With this, yeah, I would say that with this, the similar form of equations that you're going to face very soon. Okay, all right, but there are some difficulties in this. The problem is this one, because we have two types of charges. Okay, so you have two types of charge, one positive, one negative. But for the mass, you only have one type. It's one mass. There's no like no other mass. It's just mass. So there are different directions of the interactions. For the masses, you always have just an attractive force. It's always pulling toward each other all the time between two masses. But for the charges, if you have two charges, you have to determine the type of charge first. So that means if you have the similar types of charge, for example, right here in this figure over here, if you have positive and positive, the interactions will be a repulsive force. So they're going to repel each other. Sounds good? All right. On the other hand, if you have a different kind of charge, one positive, one negative, then you're going to have an attractive force. So that's it. I mean, in terms of, oh, well, it just put one more step into your analysis. You have to determine the type of charges first. And after that, you just apply the interactions law, and then you follow with the vector analysis and all this stuff. Okay, sounds good. So I mean, it's equivalent to mass in a way. However, you have more, you know, annoying conditions that it could be repulsive or it could be attractive. Depends on what types of charge that you are trying to consider. Okay, but it's easy. It's only two types, so it's not too bad. It's either attract or repel. All right, two things. Okay, all right. Now, before we move on, just, well, we're going to dive into quantitative analysis today. It's going to be a lot of fun, guys. All right, but anyway, so if you consider materials, and if those materials are allow those electrons or charged particle, it could be some material we can talk about ions moving. Ion is just like an atoms that losing some electrons or losing some charges, and then it behaves like a positive charge. But anyway, if we talk about electrons, that's our main characters here. And if the material allow those electrons to travel very easily, that's the one that we're going to say that material is very conductive, and those are conductors. Okay, so material that are conductors are the material that allow the electrons to move very easily. Okay, and that's of course pretty much metal. You use copper as electrical wires because it can, you know, allow electrons to travel very easily. On the other hand, you have an opposite type of materials. If that material does not allow the electrons to move easily, then you're going to have insulator. So that's the one, the rubber, I think that's maybe the easiest one. Glass, diamond, okay, something like that. Wood, and this is good. So those are things that, you know, if you touch it, it's pretty safe. You're not going to get a lot of electrical shock, I think. Or you can use it as, like, you know, you protect yourself from electrocuted and everything. All right, so that's an insulator. And that brings us to the third types of material. When you have material that behaves somewhere in between, when you say somewhere in between, doesn't mean like it's not so good or not so bad, but it's even better than that, is because it's sitting in between. So this allow you to do some conducting at some particular conditions, and you can have it like insulating to be some conditions. And that's, we say it's a semiconductor. But the good thing about this one is, if you somehow can manipulate this type of material to have it behave like a conductor at some conditions and behave like insulator at some conditions, that means you have some logic going on. You start to be able to build yes or no, no or yes. And that's when the semiconductors and industries got exploded like 4 decades ago. That's what it is. All right. So that's what we are doing at this point, is just so you know that the classifications of the ability of the material to be able to conduct or allow electrons to move freely in it can be classified into three types: conductors, insulators, semiconductors. All right, but of course, for those of you that about to do like computer science or computer engineering people, eventually you do a lot of semiconductor and all this stuff, right? Doing, you know, digital and then thing. All right. Oh, that's a quick comments right here, you guys. Yeah, here. This is like an advanced comment here. What about superconductors? That's so good. All right. So the superconductors was just like a very sort of, I would say, like a wonderful findings from physics experiments. It turns out when you lower your temperature of some materials, when the temperature is super low, it turns out the resistance in that material disappear. We will have a chance to touch on that superconductor when we talk about circuit, when we talk about circuits, all right? But the key is the resistance happens everywhere because of the thermal fluctuation and all this stuff. I mean, you know, your structure of the material seems to, like, you know, sort of like get in the way. Electron cannot move easily because you get stuck somewhere, you knock with its friends, or you sort of like get blocked by some atoms, all of this stuff. But once you lower your material temperatures down to almost 0 Kelvin, it turns out electron doesn't feel any blockage. It doesn't feel any obstacle. It's like sort of like, hey, I'm okay. I can just travel in this material without any body around me. I feel free. And then when electron feel like there's nothing interacting with it, then it can flow just like there's no obstacles. That's why resistance go down to 0. And that's what we call superconductors. It actually turns out to be a quantum phenomena right there. Okay, because of the, you know, there's a wave function of the electrons just spread so far away, and it has some collective properties and all that stuff. It's kind of fun thing, right? But I'll tell you a little bit more of the stories about superconductors at the time of when we will do circuit analysis. Sounds good? All right. It has some good history. It was like super boom, like what, 30, 40 years ago. Like people just, like, you know, dream about like having a circuit that can run forever. That was the day. It's like, oh wow, we found superconductors, so from now on we can charge a device once and don't have to charge again ever in your life or something like that. It will run forever. Yeah, magnet, right? All the stuff. I mean, now, when you have no friction, I mean, no friction means no resistance. It seems like things can run forever. But after some research and all the stuff, it has some limitation. So that's why the application of superconductor is limited at this point. Okay, but that's the topic of another lecture. All right, so we'll come back to our business right here. And here we go, guys. So this is After I have been talking for like 20 minutes, maybe this is too much talking at this point. Okay, here is the one that I would like you to slowly digest this one first. Okay, I have seen in the past, you guys, when you try to attack the problem right away, sometimes you sort of like, it's like you get confused by the problem itself, because of course the problems that you have to solve is going to have some complications and things. But if you grab this idea, since you're starting understanding this topic, it seems like it's going to be a lot better later. So let's sort of like keep the pace down a little bit and make sure that you understand what we are trying to do right here. Okay, so I put here one thing. The keyword over here is electric field. That's the one thing that I need from you today. I don't know one thing or not, but anyway, the other thing is electric force is going to be simple. But anyway, the key that I want you to grab today is electric field. Okay. Now, what is the field? First thing first, it's just a human device. It's like, it's not real. Who knows what's real, what's not, right? We are in like a matrix and all this stuff. Who knows? All right. But this is a theory, guys. The electric field, same thing with the gravitational field, is just physicists' way of trying to describe electric phenomena. Okay, that's first thing. So that means don't try to measure the electric field. It doesn't exist. Okay, before you sort of like, Ajahn, what are you talking about? The reason for this is, the idea is this. Okay, let's think about this. When I say, now I'm going to try to make a, like always, there will be a lot of analogy with the gravitational field. So think about this. Everyone okay with the gravitational field, the the gravity. But when I say about, hey, how do you know that we have gravity pulling down? How can you tell? Okay, don't read the comment at this point. Okay, so how can you tell? We are living in the space or in the environment that has the gravitational pull downward. How can you tell? Yeah, by me not floating around, correct. The way that you can check is you probably just have to just let yourself go and fall down on the floor. Probably that's what it is. So my point is, you probably have to have a mass and just let it go. And it turns out it's dropped to the floor. That's how you check, right? But without that, let's say, well, I don't have anything. I'm just sitting right here. What I can do is just a visualization, assuming that the Earth, this is like the whole Earth down here, do something with the environment, do something with the space around me, do something with me, try to pull me down. But the only way that I can tell is I have to interact with something and have some indications that something is pulling me down. First of all, I'm sitting right here. I'm not floating up in the sky. So it seems like something is pulling me down. So, that seems reasonable. But how can you tell? Then I can say, well, let's squeeze in like a meter, something that you can measure. And then you say, okay, all right, I can measure my weight. Yeah, vibe check. There's no vibe here. All right, so then you say, okay, all right, I'm just putting on a scale, and then there's something pressing on the scale. Then I am sure I have my weight pulling down on that scale. So it seems like, okay, it seems like it's kind of true. Earth is pulling me down because scale reads some number. Same idea with the electric field. No way that you can tell there is some electric field. The only way that you will be able to tell is you have to interact with something. But then because that thing has to be charged, right? Because we said charge interact with the charge. So if you would like to say that there is one charge, okay, let's say start with the Q here. That's my charge. And you would like to say like, hey, Ajahn, around any charged particle will generate a field. So you say like, Ajahn, around this charge, there will be some field around it. The only way that I can tell that it's true or not, I have to bring in another charge. You guys with me now? Yeah. And then you measure the interactive force. Okay, you get an idea now. So the same thing is, you can imagine like this is Earth. And you want to know like around Earth, there are gravitational pull and anything. You bring in the mass. And you say, oh, there is a pulling force, mg. Then you say Earth supposed to have some gravitational field. Cool. All right, so that's the idea of the electric field. It's derived from the electric force. So that's why in the textbook, they imagine that you probably understand it better by understand electrical forces first. And then we will introduce the fields later. But for me, you have already familiar with the gravitational field, the G, right? You already accept it. You say, Ajahn, I'm okay with the concept of there is a gravity pulling me down. So why don't you do the same with the electric field? Let's assume that around any charged particle, okay, any charge, you imagine that there's also fields around it. Just like Earth has some gravitational field. Why not? Okay, you guys with me now? That's the idea. Okay, all right. So, okay, let me read some comments just in case there is another. What about shaking gravity field by find out the bending of light? Oh, that's too way off. Oh, calm down. As I said, I'm just gonna keep the pace down a bit. Okay, so imagine this. From now on, you have a mass. You always imagine that around the mass that is field around that mass. Okay, same thing. Now you have bring in a charge. You can just imagine that around that charge, you already have the electric fields around. The only difference that you're going to have to deal with is this. In the gravity, you always have a pulling field. You guys with me? Because it's sort of attractive force. So you can imagine that you will do the same thing, except for the charge that generate the fields. You have two directions possible. Now, if something is trying to pull towards it, so you don't mind to have the arrow pulling towards it, that's fine. That's going to be one type of charge. But then if you bring in the opposite types of charge, then you're going to have an opportunity to have the field going out as well. Okay, you guys sort of with me right now? Okay, so you use the analogy with the gravitational field. But the gravitational fields only have one direction, which is attractive. So it means it's sort of like pulling towards the mass that generate the fields. But in the case of charges, you have two possibilities. There could be one that's pulling towards it and the other one that's pulling away from it. And we're going to define those directions very soon. Okay, sounds like a plan? All right, here we go. Now, what about this formula, Bojan? You put this formula in this page. What does it mean? All right, you guys look at this and I will ask you, how do you feel about this formula? If I use E to represent electric field, okay, E is for the field. F, that's for the force, that's no problem, familiar with that. And I'm going to use Q to represent charge. So this is charge. All right, so now every time from now on when we write E, that's for electric field. How do you feel about this formula? The field is the force per unit charge. That is very, very definitive. It's like, that's how you define the field. That's how they define the field. Force per unit charge. What is going on, force per unit charge? But what I'm trying to tell you is you have already used this equation before. What is the gravitational field, guys? You said G, done. What is your gravitational force? Well, John, that is my weight. What about the equivalent of the charge in the gravitational field? We said that's the mass. So of course you have done this before. Every time you use mg as your weight, you have already used this equation right here. That's how you define G. There, it's just the weight. The weight is the attractive force due to the gravitational field. Per unit mass, that's the G. So nothing can be more similar than this. It's like they are the same thing. So, done. All right, so I hope this slide alone give you an introduction of what is the electric fields. It's the same kind of fields that you use in gravity. Serious. All right. The second equation, just leave it there just for now. It's no big deal. I'm going to tell you the formula soon. All right. But that's what it is. That's electric fields. And we're going to use this analogy for the next 3 weeks or so until final exam. All right, here we go. So to make things sort of like conventional, what we decided to do is if you are dealing with positive charge, okay, positive charge, we will say that electric field will point away from it. So that's the first figure right here. So if you have a positive charge, the field that's coming out of it will be in the direction of away from the source, away from the charge. Cool. And of course, now once you define this, the negatively charged particle, we have the electric field point towards. Very good. This is our agreement. We're going to use this. We're going to agree on these directions right here. And I think everyone in this physics community agree with this. All right. All right. Okay. There's a question about N over C. We'll answer that in a little bit. Okay. All right. So once we have this, now the way that you visualize these fields, you use the line just like before. And the line will eventually translate to vector, just like what you did in the gravity. So we can call these electric field lines if you like. Okay. That is just electric field line. Okay. So now electric field lines will give you the sense of direction of the electric field at any point. For example, if I am standing right here, okay, when I look at the line, I can say, oh, electric field is supposed to point in that direction. You guys with me? Okay, not bad. If I'm standing right here, I can tell that my electric field is supposed to point in that direction. Okay, if I'm standing right here, I can say that electric field is supposed to point towards the negatively charged. Okay, so that's what we can always do with the electric field lines. It will give you the vector that representing the electric field at that point. So in conclusion, the electric field at a point will point in the direction of the electric field lines. Sounds good? Okay, nice. So in reality, you're not going to have like a single positive charge, a single negatively charged and everything. You're going to have like a combination of those. So there is a possibility that you're going to get like a complicated electric field lines. But that's okay, because can you tell if I'm asking you? If I'm asking you about the density of lines, how dense are these lines? Well, Ajahn, if you want to talk about the density, when you stay very close to the charge, yeah, somewhere around here, the number of lines per area seems to be very high. Yeah, but once you move away from it, somewhere further, then it seems like the number of lines per area is going to be smaller, because sort of like these lines will sort of separate it out and then being farther apart. So the density of lines is going to be less and less when you go further away. Sounds good? And now when I'm asking you for like a common sense, if you want to talk about the field strength, the strength of the field, you can always say, well, John, if you stay so close to the charge, you should feel the strength of the field very strong. I mean, that's a strong field. But when you run away from it, of course, you're going to feel less and less and less of that field. So the field will be weaker and weaker the further away from the source. Sounds like a plan? So it seems like there are interplay between first the distance, the R, Second, the density of the electric field lines that going through one unit area. So there is a line density, there is a distance, and it will link to the electric strength, electric field strength. So let me put like an absolute sign there. So these are the not interaction. These are the stuff that we eventually going to calculate them quantitatively. Sounds serious now, right? So this thing gets like, oh my God, it's gonna get very complicated. And this is the reason why you are about to get exposed to vector calculus. You can see now, because there's a distance relationship, there is the density of lines, there is the magnitude of this, there is the vector combinations and other stuff. So eventually you're gonna have to understand all this stuff. Okay. So with this idea in mind, the simple question that you should be able to answer right now, if you look at the figure on the right, there is an area A and B. Okay. As you can see, if you count the number of lines that going through 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, it seems like number of lines are the same. But because the area A seems like it has a smaller area, so it seems like it's a higher density. So I would say that electric field at A will have a stronger magnitude than the electric field at B. Sounds like a plan? Okay, this is the greater sign right here, greater. Make sense? The higher the density, the bigger the strength of the field. That's the idea. All right, now back to the conclusion. So we know that the further away from the charge, the field strength should be lower. Now come back to this formula right here. All right, you can ignore this first because the first part of this equation, that's your definition of the field. That is fine. Now look at the second half of this one. There is some constant right here. Okay, this is the charge. This is the source of the field. And here we go. This is the distance right there from the charge. And as you can see, it's square. That's too bad. That's where the law is. So what we are saying is the further away from the source, the smaller the electric field strength, because it's inversely proportional to the distance square. Cool? And this is, in a way, is Coulomb's law. It gives you an ability to calculate the magnitude of electric field generated by the charge Q and sitting at this distance R away from the charge. Okay? But the complication comes in here. But Ajahn, what is this R hat right there? The R hat turns out to be a unit vector that pointing in the radial direction. This is same idea as, same idea as I, J, K hat. Remember that? The I is the unit vector pointing along the X, J along the Y, K along the Z. But now R hat is also a unit vector, but points in the radial direction. So it means it's pointing in all direction wherever you want. Okay, with me? So this is weird. I would say this is the weirdest stuff that will come into our calculations. But if you go back to our figure over here, that makes sense because the R hat is this dude right here. There. Oh, I think the internet is kind of slow. Okay, here we go. That's R hat. And you can pick any direction you want. The R hat vector will always point radially outward. Radially outward. Is radially, it means it's radial in 3D. It's like in all direction. It's a spherical. It's a spherical radial directions. I don't know, is that the word or not? It's like, it's a radius along a sphere. So it means it's point in crazy front, back, up, down, everywhere. 720 angle. But it's point in all direct, I mean, in any direction that you can pick. And that is called R hat. Okay, sounds good. Okay, all right, that's nice. Okay, there's a question here. No, it's not a dumb question. What if distance is zero? Okay, that's a good question actually. When you have a zero r or the zero distance, that means you're already sitting right at that point, right at the source. That is a zero distance. And that is a very good question. The reason for that is, if I substitute r equal to zero in this expression, and we get infinite in electric field, and that is the part we say is called singularity. We're not going to talk about it because we don't know what is going on in an electron, in a charge, or in like an elementary particle. So we don't talk about that. We only talk about the effects away from it. So that actually is not a dumb question. It's actually a very complicated question. All right, cool guys. And then, all right, before we start up, take a break here, I think this is a lot of information flowing, I think. The unit of the force, everybody knows is Newton. The unit of the charge, we just said, is a Coulomb. So there's no doubt the electric field unit is Newton per Coulomb, and that's N over C. That is sitting there just for you. That is a unit right there. Newton per Coulomb. That is the unit of electric fields. Okay, sounds like sort of nice and stuff. Oh, this is always, I don't know, would this help or not, but maybe talking too much will sort of like push you further away from physics. I don't know, but I hope this gives you a grand overview of what to come. All right, don't want to speed up too fast. All right, but we're going to have a lot of fun in the second half of this lecture. I think it's a good place to take a break right here. All right, and then for those of you that really want to sort of like get a little bit ahead of the game, you can just staring at the next slide and see what is going on. I will come back and then we will understand what is this. All right, and we're about to having fun with vector analysis after the break. Sounds good? All right, so let's take 10 and then we'll see each other around 11. Sounds good? Okay, all right. All right, now let's give it a shot and see how can we apply this sort of, I hope it's like a straightforward setup for electric field calculation, yeah? So in general, when you have tons of charges building up electric fields around, so you have to do a vector summation right here. So if you're staring at this one, it's nothing more than just the formula that we just introduced, KQ over R squared. But then each one will have their own radial directions. Yeah, crazy, going point every directions. And then, of course, you just sum over I. So this equation is just a vector summation of those electric fields generated by the source I. Okay, sounds good? So for example, right here, so let's think about this. Can you understand these electric field lines from this setup? All right, let's do qualitative calculation first, shall we? Okay, so I hope this will help. I'll try to go slowly because, I mean, the reason that I would like to go slowly because from the past, I saw that some of you still apply the electric field calculation in the wrong spots. When I say the wrong spot, what I mean is this. Okay, let's think about this. If you have two charges here, one positive on the left, one negative on the right, in your head, you must assume that every charge carry its own electric fields with it at all time, infinitely super big, just like your friend just comments. It's like, I mean, I would say like this, for a positive charge, there will be electric fields line coming out of it at all time. Like that. You guys with me? Okay. And the same thing happens for the negatively charged particle on the right. I mean, it will have its own electric field. Okay, no big deal. Everyone has its own field coming out. So this is what you have to imagine at all time, that all the charges has its own fields. Crazy. It's like, okay. But then when you're asking Ajahn, what is the electric field at one single point? Okay, let's give it a shot. and see if I would like to figure out the electric field at some point. For example, here, let's do it on top right there. The black dot one here. Oh, sorry, that's a line. Sorry, my bad. Here, there you go. If I say, well, John, can you figure out the electric field at point P over here? Okay, well, okay, no problem. I have to imagine that there must be the field that due to the positive charge pointing in that direction. Can you see that? I'm drawing the line. I don't know, the internet seems slow a little bit for me, but you guys can still see what's on screen, right? Okay, so there is going to have an electric field lines piercing through the P diagonally up a little bit toward your right. And then I would say this will generate the electric field at this point P in that direction. You guys with me here? Yes? Okay. Same thing with the negative one. The negatively charged will always have electric field point out in the radial directions. There you go. Okay, but then at point P, you're going to have electric field point towards the negative charge. With me? So it means at point P, you're going to have electric field point towards negatively charged. Oh, this arrow is big. It's a wrong size. Okay, here we go. All right, this is better. There you go. Something like that. Yeah, with me now? So that means at point P, you have two electric field vectors. One's red, one is blue. Then what you want is just you want to combine these two together to get a net electric field. Okay, and then that can be done quite easily because you can say, well, oh, John, because you pick point P, that's sort of in the middle. I can do is I can break this vector into two components. Oh, there's no arrow here. Okay, so I can break this into two components. Here, horizontal and vertical for the red. Okay, and same thing happens for horizontal and vertical for the blue. See that? All right, cool. So far, so good. All right, just let me know if I think maybe internet is kind of slow here. I'm out of town at this point, so it's kind of like, it's a weird setup at this point. Okay, so now you can apply the Coulomb's law due to point P is at the distance. Okay, let me check the distance a bit. But on point P is this far away from positive charge and this far away from the negative charge. They are at the same distance. They are at the same distance. So it seems like the magnitude of the electric field seems to be the same. Okay, let me write it down for you. So if I want to figure out the electric field that is pointing up due to the positive charge, I'm going to say electric field here, the red one, is going to be K. Okay. Now there is a note coming up saying that my internet connection is unstable. All right, it's unstable right now. Okay, just chat me. I mean, put some chat if it's super lag at this point. But you guys still hearing my voice and everything okay, right? Wow, I mean, the graphic is kind of off, but okay. It's catching up at this point. Okay, all right, so the electric field is K Q over, then I have to figure out what is this distance right here. If it's R, then I would say R squared. Okay, this is good. KQ over R squared. That is fine. Now you do the same thing with the blue. Well, okay, John, the magnitude of the blue vector is going to be K. Q, if these two are the same Q, so the magnitude of the charge will be the same Q. And then you say, but John, if the distance, because you pick at the midway, so it's going to be over R squared. Cool. So that's kind of nice. Nice in the sense that now you have two vectors, the red and the blue, having the same length. When you have the same length of the vector, speaking in terms of the electric field, it means these two fields at point P having the same magnitude or strength. Electric field strength are the same at point P. Sounds good? Then you do the combination of these two vectors, you can tell right away that the vertical components will cancel themselves out. Nothing here, nothing there, because the up and the down component will have the same length and they're going to cancel each other out. So at the end, what you have left is just going to be the vector that point to your right. And this is the reason why if you zoom in, look at the orange curve, your electric field line. This is the reason why the electric field line at that point is in the horizontal direction. And your net vector, net. I ran out of color. Net. Okay, let me use the orange one. Your net electric field is going to point in this direction. Woo, does that make sense? Okay. So your net electric field will point horizontally, and that's why your electric field lines is horizontal at that point. So what I can say in speak in terms of calculus a little bit, it seems like the electric field vector points in the tangential direction of the electric field line. Does that make sense? Okay, because if you move back to where we had before, we already said, wherever your electric field line is, your electric field at a point is going to point in the same direction as the electric field line. So that's good. So that's what it is. And that's nice. Okay, so here, check. Okay, this is good, pointing in that direction. Here, it's going to point in the same direction as the electric field line. That's so far so good. And now if you have a curved one, then you say, well, John, no big deal. If I would like to find electric field at this point, it's just going to be a tangential direction to that. Tangential direction to that. Tangential direction to that. That's what these electric field lines and the electric fields at a point are related. Okay, so I hope you see like a grand picture of what is about to happen. But when we do the actual calculation, we do it at a point. So that's why you have to have some connections between calculation of the net electric field at a point and the grand sort of like scheme or whatever the diagram that you usually get when you try to draw the electric field lines for the whole system. So that's what it is. Okay, sounds like a good plan. Okay, let's come back here. So let's look at the figure on the right most, for example. This one complicated, but you don't have any role of doing this. You don't need to sort of like draw a diagram of electric field lines or anything. But at least now you understand that if you are given a electric field lines that looks like this, and you say, well, John, what is happening at the point? Then you can say electric field is going to point in the tangential direction right away. Okay. All right. And here you can pick any point and you just draw a tangential line to it. And that will give you the direction of the electric field at any point. At any point. At any point right there. Cool. That's not bad. Okay. So now you start to see that, I mean, of course, it's going to be computer generated. You're not going to supposed to do it by hand. However, what you actually do is you just calculate the vector summation at a point and you keep that value there, and then you do it to the next point, the next point, next point, and then you do the connected lines. You get electric field lines from your vectors at each individual point. Okay, cool. All right. So I don't know, in the modern visualization, I don't think you really need to do, I mean, you do both actually. It depends on your visualization, right? Sometimes you can draw something, we call it like a vector diagram or a vector plot or something like that. I'll show you next time when we do some more sort of like a summary of everything by using some simulation and stuff. You have another example of writing this down. But at this point, let's try to do actual quantitative analysis. Okay, sounds good? Let's give it a shot right here. All right, guys, it's getting serious a bit. No, not too bad. All right, we're just going to do vector summations for a few examples, and then I think we call it done. Not too bad. Okay, 3 equal positive charges Q are at the corners of an equilateral triangle of side A. Right, so that's your setup system setup right there. What are the magnitude and direction of the electric field at P? They want it at the top of that triangle due to the 2 charges at the base. All right, I intentionally want this to be the first exercise. Really want it because this is kind of like will throw someone's off a little bit by asking the electric field at a point where there is a charge sitting there already. Isn't that cool? I don't know if we call it cool or not, but anyway. All right, the point is they want you to figure out the magnitude of an electric field at point P. So first thing first, to me, it doesn't matter point P has a charge or not. I don't care. I can just erase this charge on the top. Doesn't matter. Because what I want is I just want to get electric field at point P due to the other 2 charges at the base. Yeah. Sounds good. All right, so let's do what we just did. We said every charged particle comes with electric field around it. So the first one will have electric field pointing radially outward. So let me draw like, this is like overdraw things, exaggerate it a little bit in terms of like necessity drawing this, but just want to make sure that you guys get this. All right, so the positive Q charge on the left will have its own electric field around. But what we are looking at this point right now, we want to know what is going on at point P. So electric field will point in that direction. Let me call this E1 then, vector. Sounds good? And it's going to point outward because the Q is positively charged at this point. Okay, now move on to your right-hand charge. The right-hand charge will have its own electric field lines as well. So it's positive charge. It's only a single charge, so it will have its own fields piercing out. It's not piercing anything, it's just like radially outward. Okay, cool. But then at point P, because this charge is also positive, electric field will point in the outward direction. So let me use green, or actually I can use blue for that. Here we go. There you go. With me? Oh, that's off. Here we go. All right, here you go. There you go. Nice. All right, and to figure out the net electric field at point P, all you need to do is just sum these 2 vectors together. That's your task. All right, let me call this E2. All right, first, let's figure out what is the magnitude of E1 electric field. Number 1, it's going to be K. It's going to be Q, the charge that's generating the field, divided by the separation or the distance from that charge to the point of calculation, which is A squared. That's it, guys. That's the magnitude. And the direction is this direction right here. So even want to overlay my R hat just to showcase what the R hats mean. It's going to be like here. That R hat is right there. It's a radial direction. Okay, so I can also write this one equally, just like KQ over A squared R hat, if you like. But to me, just magnitude of E1 along with the diagram that's showing which direction E1 is pointing to, I think that's more than enough. That's already good. Okay, so you do the same thing with the E2. Let's figure out the magnitude. It's going to be K. The charge generating the field is the same, Q, over the separation over here is also A. That's A squared. Same magnitude, of course, because same amount of charge, same distance from that charge. So you're going to get the same magnitude of the electric field, but it's going to point in different direction, of course. All right. So, and if you like, you can write this one as a vector equation if you want. And this is R hat, see? So these 2 equations look exactly the same in the vector formats because you have an R hat that is just a unit vector in a radial direction. That's why. Okay. But I mean, when you look at the diagram, of course, red is pointing sort of toward the right, blue point toward the left a little bit. So that's what it is. Now you just have to figure out the net electric field. Okay, let me put R hat here too. Sort of, that's what it is. All right, and actually you can put R hat here too. I just want to make sure that you understand what the R hats means. It's just you can bring your R hats anywhere you like. You can, go to campus, you go to MUIC or whatever, your R hat is still radial directions. Yes, all right, that's really the next thing. All right, and then now you want to make the final summation of these two vectors. Now you can come back and do just like what you did. It's just two vectors in combination. So what I'm going to do is I'm going to break E1 into two components, horizontal and vertical. Looks good, yeah? All right, and same thing happens to the E2. I'm going to do horizontal, vertical. There you go. Eliminate that. All right, here we go. Now, because this is the equilateral triangle, so you know that the angle down here is going to be 60 degrees. They're all 60 degrees. So this is going to be 60 degrees as well. It looks dirty now, but I think everyone gets the geometry did. It's not too bad on this one. So what you get over here is for the top, the rate vector E1 will give you E1 sine 60. For the blue, you're going to get E2 sine 60. Well, the horizontal component will sort of cancel each other out. So this one is gone, no big deal. So the net electric field at this point, I would say net electric field at point P is going to be E1 sine 60 plus E2 sine 60. And then it's going to point upward. So I can say point up like this and say this is my vector equation. Looks weird, but that's all right. it's non-conventional way of writing a vector format, right? But it says I have an arrow says pointing up. So I think this is good. All right, because E1 and E2 are the same, and you know the value of the sine 60. So what I can say is just going to be twice of the KQ over A square, and then sine 60 is square root 3 over 2. 2 cancel, and that's it. So it's root 3 KQ over A square. And then now you can use your conventional way of writing the vector that is pointing up. If you want, you can say it's a J hat if you like. If we call this X and Y. There you go. And that is done. It's supposed to have like a sound effect right here, but that's what it is. No sound effects today. All right, everyone just sort of like follow this whole thing. It's a vector summation. And to get each vector, you just have to apply Coulomb's law. But because at this point, we are not talking about the force just yet. We're just trying to figure out the field around any charges. So what you need is just figure out the point of interest is how far is the point of interest to the point, to the source that's generating the field. That is your R, the distance. What is the magnitude of the charge? Once you get the Q, once you get the R, KQ over R square will give you the magnitude of the field at that point. Simple enough, I guess. And now another point is you can calculate this with or without the charge at the top of this triangle, right? See, over here, we are doing it without caring what is going on at that point. At least now we know how to calculate the fields at that point. Okay, cool. Any questions so far? I think it's not too bad. Let's try again, shall we? Okay, we're going to do less and less drawing. Those like, springing out of the electric field line seems kind of like dirty, yeah? Okay, try again, guys. Figures shows two charged particles on x-axis. Now one is negative, the other one is positive. Now the value of the charges are given. X is also given, 3 meters. All right, so let me sort of put some distance there, 3 meters. Okay, and what are the magnitude and direction of the net electric field produced at point P, which is 4 meters high, which is why it seems like that's a good geometry there, 3, 4, 5. All right, so we do the same thing, but now I'm going to draw a little less here. So let's start from the positive Q charge on the right. it will generate electric field. Oh, sorry, it's supposed to be a line here. It's going to generate the electric field point in the radial direction here. With me, I'm drawing the line right there. There. Okay. And at point P, electric field is going to point in that, is off, in that direction there. Let me draw like a big one here. There you go. All right. Now, let's pay attention to your left. The negative Q charge will generate electric field along this radial line. But because it's a negative charge particle, the electric field will point towards it. So it's going to point here. You guys with me? Okay. Oh, now you can guess now these two lines, these two vectors are supposed to have the same length. You probably can guess now. All right, but this is what it is. Okay. Positive charge generate fields pointing outward. Negative charge generate field point towards the source. All right, now let me name the green one to be E1. Oh, let's do E positive, why not? Yeah. And then let's call the blue to be E negative. Yeah. All right. All right. So that's your E positive and E negative vector. Okay, now we can calculate the magnitude of the E positive vector there. It's going to be K times the charge generating the field, Q, divided by the separation from the charge to the point of calculation. And in this case, you can say this is 5. It's 3, 4, 5. So it's going to be 5 squared. Done. Okay, cool. All right. Blue, the negative electric field here is going to be K constant. Q is the charge generating the field right there, divided by same distance is also 5 squared. No big deal. Now you want to figure out the net electric field. So you do the same vector analysis here. You break this into two components, one horizontal, one vertical. Same thing with the blue, one horizontal, one vertical. But because you're dealing with the same sort of like mirror image between the green and the blue, the vertical component will cancel themselves out. It's gone. Okay, that's fine. Now you're only left with just the left pointing vectors from the horizontal components. So let's calculate that. So this is going to be E plus. Now it depends on what angle you want to measure. If I'm going to call this theta, that will be my theta. That will be my theta. So this is going to be E plus sine theta. All right, you can name whatever angle you like. That's up to you. Okay, the blue will give you E negative. Okay, let me put that absolute sign there too. And it's going to be sine theta as well. So for this case, okay, the vertical components cancel. You only left with just the horizontal components. So the net electric field on this one is going to be E1 or E plus, sorry, sine, but sine is just the opposite over hypotenuse there, so it's 3/5. There you go, plus E negative. Oops, it's not supposed to have sine there anymore, sorry. It's already 3/5 right there. All right, okay. Oh, okay, let's erase them all. Sorry. Okay, one more time. E plus, okay, let me put sine theta here first. Sine theta plus E minus sine theta as well. All right, those are the two that you want. And then you just substitute in the value. Is going to be KQ over 5 squared. Sine theta is going to be 3/5. And you have two of them. They are the same. So I can just multiply by 2. There you go. All right, and the rest, you can just plug in the value. And then you get the net electric field magnitude. But then because you want to have them in terms of like the vector, because they're asking you both magnitude and directions, I can turn this into a vector, bam, and just say negative I hat. You guys with me? If I name this to be X and Y, just a regular one. But in the exam, you can say point to your left or point to the negative x direction is fine. You don't need to use ijk notation to specify a vector direction. You can use whatever you like. Okay, it's no big deal. Can I just draw an? Yeah, that's fine. If you draw an arrow, I think that's good enough. Okay, see, it's not that bad, right? It's just sort of like bring you guys back to the vector analysis a little bit. The only thing that's add on top of whatever analysis that you're doing is just the Coulomb's law. Okay. However, well, to be exact, then we talking about the electric field, but I call it Coulomb's law anyway. They are the same thing. Okay, so just to be complete in terms of the material that we mentioned, we haven't talked about the K much. So it turns out the K is another constant you have to deal with. Okay. Okay, so this constant, it's already put there. The value of this K, where, okay, not yet. It's gonna be put up next. Here we go. All right, it's gonna be flash forward into like a few slides. Okay, here we go. So there is a K. This K is gonna be called Coulomb constant. But because eventually we're going to get to the Coulomb's law, so we can emphasize on this value again. But let's think of it as one constant at this point. Don't worry about it yet. Okay, sounds good. All right, so let's look at questions here. Can I draw an arrow? Yes, not that bad. Final exam 8 charge part. No, never done that. I think the worst that ever happened was six charges with a highly symmetric arrangement. So it should be fine. All right, scatter with one on a paper with no symmetry. Oh, come on, man. All right, try one more, guys. Just sort of like bring everything down to this one. Let's say if you have like a free floating orientation of the system, right? You're not sort of bind to X or Y axis or anything. It's just sort of like some arrangement of now four charges. So in the figure, 4 particles are fixed in place and you are given Q1, Q2, Q3, Q4 with the sign attached to them. Distance D is also given to be 5 micron. What is the magnitude and the electric field at point P? You want to give it a shot, see how it goes. All right, try it, guys. I'll give you like 2-minute head start here. Okay, point P, you want to figure out the net electric field. You want to get the net electric field. And it's supposed to be simple though, because I'm not just going to ask you to do like crazy vector summation or anything. It's just going to be, you know, a lot of cancellations here and there. Eventually, you're not going to have to calculate much. Okay. All right. Slowly go through these one by one and you start to see something here. Okay, very good. So in the meantime, while you're thinking, I can say Q1 and Q2 having the same magnitude. That's nice. When Q1 and Q2 are having the same magnitude, that means the electric field, okay, let's do this. I have to do the color coding here. So Q1 over here at P will generate electric field pointing outward. Let me point it here. You guys with me? Let me call this E1. Yeah? Because it's positive charge. So electric field point away from the source. Okay, and then Q2, let me use the red one here. It's also positive. So at P, electric field due to point E2 will point outward here. That's E2. Cool. But then you can see by symmetry that the distance between Q1 and P, Q2 and P are exactly the same. Charge Q1 and Q2 are also the same. So you are guaranteed that these two vectors is going to cancel themselves out. Perfect. So that's out of the picture. No need to do anything else. All right, now move on to Q3. Your Q3 is still positive. So let me use blue here. That's positive. So the electric field due to Q3 will point radially outward, right? At point P, it's going to point down here. You guys with me now? I don't have to draw like a straight line having like a radial guideline anymore. I think you guys can visualize in your head now. So it's going to point radially outward away from the source, which is Q3. So it's going to point sort of diagonally down here, and it's E3 right there. Very good. All right, now Q4 is negative 12E. So that means the Q4, let me use some different color. Let me use violet here. So that's Q4 up here. Now is negative charge. So at P, the field will point toward the source. So it's going to point radially up like that. Let me name this E4. But we don't know the magnitude of the E3 and E4 yet. So let's calculate those. E3 magnitude is K times Q, the source. Q3, let me put 3E. And you know what the E is. It's just the charge of one electron. So that's a number there, 1.6 times 10 to the negative 19. But let's name it E for now. Divided by the separation from the source to point P, which is 1D. Let me put D square right there, you guys. Good. All right. So at least you have a magnitude weighting the blue E3 vector pointing diagonally down. Now, what about E4? Right there. K, the charge generating it's Q4, 12E, divided by, now the separation or the distance from that to point P is 2D. It's 2D. Now you take that and square them. So that's 2D squared. And this gives you, whoa, same magnitude again, guys. Isn't that nice? So at the end, it turns out E4 and E3 also have the same magnitude, but pointing in the opposite direction. So they are also canceled. So answer is the net electric field at point P is just 0. Dot. Not bad at all. All right, so I hope you see how to manipulate the electric fields now, and also how to calculate the electric field magnitude. Plus, how can you determine the direction? There are only two cases. If it's positive, electric field pointing radially outward from the source. If it's negatively charged particle you're looking at, electric field point towards it. Yeah? All right. And now there's one observation that you probably have already seen here. During the calculations, if you notice, while I'm talking about the positive charge here, Q3 is positive, I plug in the positive 3E here, right? But then when I look at the Q4, Q4 is negative 12E. But when I do this calculation, I didn't put the negative anymore. This is the reason is because the positive and negative charge will give you the direction of the field, but not related to the magnitude. So you can think of it like I'm just putting the magnitude of the charge right here. So that's why no matter it's a negatively charged or it's a positively charged, you just plug in the magnitude of the charge. Okay, and your directions you just determine by the sign of that charge. Sounds good? So it's not bad. All right, so if you look in the past, no matter you looking at the -1 or +1, when I plug into this Coulomb's law, I just plug in the Q. I don't have to put extra negative sign anymore because there is an absolute sign right here on the left. Okay, so, or you can imagine like when you try to look at the vector, you do the calculation separately, one for magnitude and the other one for the directions. The magnitude stick with this Coulomb's law. Directions look at the type of the sign of the charge, something like that. Okay, not bad. All right, that's pretty cool. So I think that's pretty much in terms of the calculations that I want to give you today. And just before we conclude this lecture over here, that's something that sort of like keep in mind here. I don't know, is this good or bad? Maybe it's too much or it's just all right. But anyway, I'm just gonna let you know what is going on. First, this one's check. Now I think everyone up to this point understand what it means by if you have any electric field lines, you can always be able to determine the electric field at a point by looking at the tangential direction. Okay, so conclusion, the direction of the electric field is tangent to the field lines at all points. Okay, second one, we already discussed this earlier. When you look at the place where the field line is dense, you have a high density of lines. And when you look at the area that the line is pretty weak, you don't have a lot of density in that part. This one, the one that has a high density, will be interpreted as a strong electric field because you have like a super like big numbers of line per unit area. So this means the strength of the field must be high. And in the portion where the density is low, that means the electric field strength is going to be weak as well. Okay, so that's check. All right, that's pretty good. Now, number 3, electric field starts on positive charge and ends on a negative charge. So we agree on that because that's what we started out. We say electric field coming out from the positive charge. And when you have a negative charge, it's piercing in toward the source. So that's why you can imagine, in a sense, we'll talk about this in maybe next week or 2 weeks from now. You can imagine that the positive charge is the starting point of the field lines if you want to. And you can think of the negative charge to be the ends of the lines. Or, in other words, you can think of the positive charge is the one that tries to generate the field. But it's not like dynamically generated, but it's, you know, the field coming out from the positive charge. And it's going to end that sort of like it's moving and then it's sinking into the negative charge. All right, either way you want to imagine, that doesn't matter. But the point is, electric field lines coming out or starting from the positive charge and ends on a negative charge all the time. Okay, very good. And the last one, you will never have a chance to see lines crossing. That makes sense because you're not supposed to have a crossing lines because you're supposed to have like a net electric field at a point. So this one is impossible because if you have a crossing point, then you don't know which direction you want to draw the electric field line at that point, because we already had agreement that electric field vector point tangential to the field line. So with the intersections, there's no single tangential line, so it's kind of impossible there. Okay, so that's check. Okay, all right, cool. Or there's a question comes in, the field seems to cancel out so well, but when I try to balance, the magnet is near impossible. Oh, okay. All right, well, because in the magnetic field, a short answer is you have a high instability field. The structure of the field is very not stable. So that's why it's so hard for you to sit there and then sort of like, well, have it sit there all the time. So you can think of it like a bowl. The bottom of the bowl is a stable point. So you can roll a marble there and it's going to stop there at the bottom of it. But then if you flip the bowl upside down, right, the peak, the top of the bowl is still an equilibrium point. You can place a marble there. But then, as you can see, if you move yourself away just a little bit from the top of the bowl, the marble will just like roll down. So that's what the stability means. Okay, so in the magnetic field, it's so hard for you to get a stable point. That is, there's a name for it. I don't remember from the top of my head at this point. But there's a bowl upside down and right side up that give you different kind of equilibrium points. So that's why it's harder. Okay, but the electric field seems to be easier because you get a bowl like that's a regular bowl. So a charge can sort of fall into the bottom of that. Well, we'll talk about potential energy, and then you'll have a chance to look at the landscape of the electric field lines and all this stuff, or electric field potential, and then you'll see that there's a valley and there's a peak and all this stuff. All right, it will be clearer when we discuss in terms of energy. Okay, all right, so I don't know if this is a short answer or not, but anyway. Okay, so that's what is the characteristic of the electric field lines. But anyway, in the exam, it's going to look something like this. It's going to be like, hey, you are given a set of charges, and then, hey, what is the electric field at this point, at that point? What is going to be the magnitude and the directions of the electric field? And that's it. Okay, sounds good. All right, so I think that's pretty much, I'm going to leave you here with the last slide over here. Is just now, once you get to the field E, your job is done for the force. And that's our business next time. It's going to be super simple. Once you rearrange that equation one more time that we just said, electric field is force per unit charge. You just move the charge to the other side. You say force is just the charge times the field. And this, we're going to make like a sort of like analogy again with the gravitational field. The weight is just mg. And you're going to see that everything is going to be like a super simple extension from electric field calculation. Sounds good? All right, guys, that is it for today. I hope you learned something. Maybe it's too much already. All right, guys, take care. All right. If the sort of like, I don't know, like audio is sort of like a little weird, that's because of like, yeah, I'm from somewhere else here. Is it the same date as on Sky? Okay, actually, okay, that's a good question. I already disabled the final exam. So actually, we can set our own date for the final exam. So it should be fine. Yeah, I just already disabled them. Yep. And it's going to be the same format. You like that, I think. Just take home 8 hours. Yeah. All right, guys, take care. I'll see you next week. Yeah. All right. But anyway, toward the ends of let me talk about that. I might need to have a makeup lecture. So I'm not sure you guys free on this Saturday. I mean, is that all right if I have like a extra? I mean, if you guys can make it, if not, then you can catch up with the YouTube playlist and stuff. Okay, all right. So if some of you can make it, then all right. So I'll set it up on Sky System, and we'll have a makeup lecture this Saturday in the maybe in the morning, just like before. Yeah, like 10 to 12. But for those of you that cannot make it, just catch up with the YouTube video and stuff. Yeah. All right. Thank you. All right. So we have to probably like do once or twice makeup just to make sure that we cover the lost time that we had. All right. Thank you, guys. I'll see you guys next week. Yeah. Oh, I'm sorry. This Friday for those of you that can make it. If not, for the rest of you, I'll see you on Monday. All right. Bye-bye. Take care.